breakdown on test number 4. And that will cover polymers, lipids, which is fats and oils and steroids, and carbohydrates. And one of your colleagues asked about what should you study for polymers since there's no polymer problem set. Well, there's not much to study other than you should know what's the definition of a polymer, which I went through in class. You should know what's an addition polymer, what's a condensation polymer. And I'll go through this on Tuesday again when I do my review. And you should also know what's thermoset, thermoplastic. And what I mean to know is, example, thermoset is a polymer once made, can't be machined or reshaped. And you should also know examples for those, which I mentioned yesterday. Example, car tires are addition polymers, and they're also thermoset polymers. Plastic water bottle here, or any water bottle or plastic bottle, well, not any, but these are a condensation polymer, meaning it has two different monomers, types of monomers being used to make that. And it's also a thermoplastic. There's no relationship between this is an addition or a condensation, and is it thermoset and thermoplastic. And that's all you have to do, so I can't really ask any more questions than I just did now. All right. One of the things what I want to do today is go through and cover some things. I'm going to pick up the pace today a little quicker than I normally go, but I'll come back and cover it on Monday and Tuesday, and even Wednesday, so plenty of time to go over it again. For those of you who had lab on Tuesday, you learned something very special that people don't tell you about me when it comes to camera, and that is, put a camera in Dr. White's hands and he goes to her. And since I'm not getting released, this is for my personal thing, and I only have 505 more shots I can take on this slide. For you people in the back, well, that's the nice thing about having a large flash drive. You can take tons of pictures, and if they don't come off, right, you just delete them. All right, I've got a lot to do today. Otherwise, I'd take another 20. All right, yesterday I was talking about carbohydrates, and we're talking about the fact that I went through a reaction that you had learned for test number 2, which is a reaction of an aldehyde or ketone with an alcohol. And while I'm pulling this up, another commercial from Dr. White, a public service announcement. 1, Monday I'll be going through the lipids problem set. And 2, don't forget, a week from today is the deadline for the extra credit project if you're planning on doing it. It's optional, you don't have to. But if you are, I'd highly recommend you bring it in Monday or Tuesday or even Wednesday and have you check it so you can change things so you get your 10 points if you want.
I have a question about that. Is it by the end of class period or by the end of like lab?
By the time I walk out the building,
Okay.
I'll give you that. In other words, if I'm in the parking lot, that's too late. By the way, did anybody happen to think that your left shoe is chiral? All right, let's take a look at this. If you look at this, I have D-glucose, and that's the Newman projection, which you don't have to write down. Now, try this with a marker that hopefully works. Success. And you learned this for test number 2. Take a ketone or aldehyde of R prime is H, it's an aldehyde react with an alcohol acid catalyst, you'll get a hemiacetal hemiketal. Normally, you see how my software tests, I'm going to write an aldehyde, in this case glucose, but I'll write it this way right now so you can see what I'm about to do better. Remember, this is carbon number 1, carbonyl carbon of an aldehyde. In any molecule, when your numbering is 1, 2, 3, 4, this is carbon 5. Notice carbon 5, which I have in blue, is an alcohol, carbon with a hydroxyl group. So really, it's that. This carbon is part of the R group. These are just connected together right here with my aldehyde. Now it turns out when functional groups are in the same molecule, that's called intramolecular. In the same molecule, since they're close by, they react quicker than when they're separate molecules. So it turns out there's an equilibrium. You don't even need a catalyst. All catalyst does to make a reaction go quicker. That this will react like that. Now let's take a look at this. What's really happening? The oxygen here from the alcohol is attacking the carbonyl carbon, opening it up to an alcohol, and this oxygen will be on that carbon. The R group is still attached. So if we look at this, same thing happens. Now, watch what happens. Whatever is not affected, you've learned this semester, this comes along for a ride. This isn't going to change. So let's do this. This here is unchanged, and all I've done is copied it over. The new thing is this hydroxyl group will attack this carbon and form a carbon-oxygen bond, which is this bond. And then what will be on that carbon? Hydroxyl group. And if this didn't happen, we would never have any of the starches you're used to consuming. There'd be no bread, there'd be no rice, there'd be no good stuff like potato chips, french fries, and other things. This is extremely important equilibrium, not a new reaction. Hydroxyl group alcohol attacks the carbonyl and forms this. Now, if you're a carbohydrate chemist, you're going to write it this way. This is the same structure. This is called the Newman projection. Students have trouble with that. Chemists, some have trouble with it. A long time ago, I figured, how can I make it easier? Well, have the longest, ugliest carbon-oxygen single bond drop that way. Makes your life easier because know this. It's subtle Thursday. On a test, if I put this, which is glucose, which I will never ask you what's the structure. I would put this and give the organic product the products, and I put a double-headed arrow. You should know how to get to this. Since on test number 4, there'll be 1 or 2, I forgot, in the process of writing it, synthesis problems. If I put this double-headed arrow and a question mark here, you should know how to go back to this, just like we've done before in synthesis. So you should know this. Let's go through it again. Aldehyde, alcohol. When they're separate molecules, you need a catalyst to make it go quick. When they're in the same molecule, you don't need that catalyst. You form a hemiacetal or hemiketal. Notice what's attacking the oxygen, alcohol attacks carbonyl carbon, opens it up to them. If I come over here to glucose and look at this hydroxyl group, that's the only one that reacts. This attacks the carbonyl, opens it up. And this oxygen here is that. Here's my R group. Here's my R double prime. The hydrogen is there. I drop the group, and that's how that happens. And you'll see in a little while why having that happen is so critical. And it's so critical, that's why I want you to know it. Now here I have the structure of fructose, and I've written it again on the board. Remember, glucose has an aldehyde, it's an aldose. Fructose is a ketose, but this is just a ketone. And same thing that I have written over there still is true. Take an aldehyde or ketone, react it with an alcohol, acid catalyst, you'll get a hemiketal, hemiacetal. Carbonyl carbon comes this carbon. The oxygen attacks the carbonyl carbon bonds to it and opens it up. Well, guess what I have here? Carbonyl, carbon, carbon, ketone. Again, 1, 2, 3, 4, 5, and in Mother Nature's world, which we all live in, it's only that hydroxyl group, because that forms the most stable ring energetically, which I haven't had a chance to cover in this semester, but that's one of the reasons, driving force. And again, equilibrium, because you have an intramolecular reaction. And what's going to happen? All right. Just like that general reaction that you know, this will attack the carbonyl carbon. What's not involved in the reaction stays the same. I'm going to show the carbon right there. Normally you don't. And what's not reacted, I just copied. What will react is this becomes this oxygen, which is bonded to what was my carbonyl carbon, and will open up to this alcohol. And again, know the reaction, but it's in the same molecule. It's a little more complex you're used to, but this is real life. And here you have fructose, which is a ketone, ketose, reacting with the C5 hydroxyl group right above CH2OH to open it up just like this one. And again, being Subtle Thursday, know this. If on a test I put this, equilibrium, give the organic product or products, you should know how to derive this. On a test, if I have that in equilibrium, leave this blank or a question mark, what would be the starting material? You should know how to go backwards to this. You've learned that. I'll cover this again on Monday and Tuesday. This is the way you'll get it. But it's really important. If this didn't happen along with that, we wouldn't have any table sugar, which would be a sad thing. Life wouldn't be as sweet. Yes, ma'am.
So when this happens, they are becoming rings, correct?
Right. This is, how should I say this, a very ugly way of showing a ring. If you were a carbohydrate chemist, this ring would look like that. Now, which is easier for you to draw and understand what's going on? This or my drawing? If you notice, this carbon here with the hydroxyl group, this alcohol in C5 reacts as a ketal, and which is easier to see, that or that? And that's why I'm teaching this. Because when I taught that or tried to, it didn't work well. And I want things to work well. Like I said, I'll come back to it. All right, next one, reduction, C-board. Oh boy, I better get to work. Again, you don't have to learn, memorize the structure, but this is glucose, most abundant sugar in nature, and it's an aldehyde. And from test number 2, if you take an aldehyde or ketone, react it with hydrogen catalyst. Remember, this has a pi bond. What can you do with hydrogen, a pi bond? Break it. Each atom of, in this case, a double bond, gets a hydrogen. Again, you learned this for test number 2. I had a problem or two like that on there. Well, what if you take this and react it with, say, hydrogen and nickel? Hydrogen, the catalyst. Anybody here know a reaction with hydrogen and an alcohol? Because I don't. In other words, it doesn't react. Anybody know a reaction of an aldehyde with hydrogen and catalyst? Ooh, it's on the board. So, whatever doesn't react is still the same. And all I've done is redrawn everything below my hand. This has one hydrogen to break the pi bond, and you'll get this. And I can rewrite this as CH2. And if we look at this, That molecule is called, the common name, sorbitol. And one of the things I've been asking you to always question is, why are you learning this stuff? I don't know why they make Yahoo the default engine. And if you look here, they're showing stereochemistry, but what is sorbitol? 6 carbons, each one has a hydroxyl group. Here it shows you the actual stereochemistry, not in a Fisher projection. And what do you use sorbitol for? It's an additive in many over-the-counter remedies. If you buy cough medicine or other things, they'll have sorbitol in there. And what does sorbitol do? It gives things a sweet taste. But it's not truly a sugar like glucose or fructose, and it's also a thickener. And therefore, if you're buying something over the counter that's a liquid, and you pour it into a little measuring cup or a teaspoon or tablespoon, and you want to get that feeling, this is good stuff, will help me. If it's thin like water, well, I don't know, but if it's nice and thick and viscous, ooh, this must be good stuff. And they play that game. And why is it thickener? Because of all the hydrogen bonding it can do with water. And how is it obtained? By the reduction. This is called the reduction. I also, when I taught to call that a hydrogenation of glucose, and I can get glucose from many places, including corn oil or corn syrup. And next time you happen to be home or in a big box store that sells over-the-counter remedies, and even some prescription stuff that are liquid, look and see for sorbitol, and sometimes even solids. All right, don't copy the slide down. It's just meant to remind me what to do next. And now, these are called glycosides. Well, not this one, but the cyclic, right here is a glycoside. And you can react that further to make something, and that's why I have, remember, the reaction with methanol. Test number 2, I showed you the following reaction. Take an aldehyde or ketone, react it with not one, but 2 molecules of an alcohol acid catalyst, and what you get is an acetal. Now, what I didn't show you then, and I'm going to show you now is, you know this reaction, which I just had on the board twice, aldehyde and ketone, 1 molecule of an alcohol with alcohol, or 1 molecule of alcohol with acid. You'll form the hemiacetal. And what happens next is this reacts with the second alcohol molecule and acid to replace this hydroxyl group with OR. It's called an alkoxy group. Now, if you notice, both R groups on the oxygen are the same. And we call that in organic chemistry symmetrical. But if I can make this compound, which I can, with only 1 alcohol, what if I react it with not the same alcohol, but a different one? That turns out you can. And what you do here, you replace the OH with OR, but now different alcohol. The second one is now R triple prime, or whatever you want to call it. And this is not the same R groups on the oxygen, so we call this unsymmetrical acetal or ketal. Now it's time for me to remember the reaction with methanol. And the following, which I'm going to teach you, is extremely important, which has been on as I just showed you over there. If you take a hemiacetal, hemiketal, react it with a different alcohol, or any alcohol really, but different than what's already on in the molecule, you'll replace this OH with O triple prime. And if you look at this molecule, what is it? Well, you just saw how to make it. This is a hemiacetal. Carbonyl, which became this carbon, hydrogen, R prime. This I'll call R double prime. Hydroxyl group, oxygen going to R. So really what this is that. And if I react this with an alcohol, say methanol, see I didn't forget, well, so I have my slide there, and acid catalyst, this hydroxyl group will be replaced by this. And actually that oxygen, not this one is on there, but you don't have, when you write it down you don't show that, but so what's my R triple prime in this one? Methyl. And what happens? Everything attached to the carbon with the hydroxyl group stays the same. There you have that. What changes? OH becomes OR. What's my R group? Methyl. And this reaction occurring not with methanol, but I'll show you something else, is the basis Mother Nature uses to make all starches. But you know something? I haven't given you a chance yet to try something on your own. What would be the organic product or products for the following? While you're doing that, I can be obnoxious with my camera again. let's take a look at this. What do we have? Ooh, alcohol, alcohol. Did you know the reaction of an alcohol with another alcohol like this? No. But this is a hemiacetal. Or it could have been a hemiketal. So the only thing that's going to change is this right here, so I can rewrite everything. The only thing that's going to change is this hydroxyl group. Will be replaced by the alkoxy group, OR triple prime. What's R triple prime? And propyl, and carbon has the hydroxyl group. And there you go. All right. What I'm going to write on the board, do not copy unless you want to, you don't have to, but it'll help you understand something. And I figured I needed a little more space. All right, if you notice, I have not one, not two, but 3 glucose molecules. You don't have to write this down, and I'll explain why in a little while. It's not today, Monday. But if we look at this, I have this right here, which I erased some of it. Hemiacetal, and I showed over there it can react with an alcohol. Which alcohol? This one, and another glucose molecule. And what happens is, this oxygen, which is this oxygen, forms this bond to there, and it's actual bond, not an arrow, and this is connected together. Now, if you look at this new molecule, 2 glucose molecules connected together by an acetal linkage, this is an acetal, I've got another hemiacetal. And in this molecule of glucose, I've got that alcohol. Same thing happened. If I had another molecule of glucose here, I could hook it together. I could keep on going on and on and on like the Energizer Bunny. And what really you're getting is a polymer of glucose. We have a name for that. When N plus the N1s are about 100, we call that starch. And what Mother Nature does, or did and does, is link glucose molecules together when it's in the hemiacetal or glycosidic form to form this polymer, which we call starch. And plants use it, we use it, animals use it. It keeps us alive. It does many things in our body. Now I'm well beyond my knowledge of biochemistry, but this is very important. So what I would like you to remember is two things. One, what is starch? It's many glucose molecules linked together. Two, the link is acetal, I guess you call it bond or bonding, which is this right here. And you know the chemistry of acetals. So I'm never going to put on the test that would be cruel and unusual punishment, but you should know something like this. Now normally here, use an acid catalyst. Mother Nature has special acid catalysts. What do we call those? Enzymes. And a lot of the enzymes are just fancy H+. Isn't that? If I were asked on a test, give the name or the structure of the following reaction. Ooh, 50 glucose molecules with another 50 acid. What's the name of that? Because I'm not going to draw it out. Starch. Now we're getting into your everyday chemistry, things that are going on all around you. Now, one other thing. Mother Nature is very versatile, and turns out once in a while she can use this alcohol to react in this reaction. This way you get a straight polymer. When some of these are there, you get a branch polymer. And example of that would be straight pectin, and this won't be on my test or the ACS. And when it's branched, they call that amylose pectin, different types of starches. And they have different physical properties, which you can look up on your own, but it makes a difference, and it makes a difference if you're cooking with different types of starch. And flour is made up of glucose. Now, do not write the structure down, but what I'm going to tell you, you should know, sucrose, table sugar, that's made from the reaction of this acetal, hemiacetal of glucose with the hemiacetal of fructose, same type of alcohol acetal reaction. And it looks like this, but what you really should know is the following. Again, the enzyme, the H+ is usually in your body or elsewhere in Mother Nature. An enzyme, which is really H+, you take glucose and fructose and react together, what do you get? Sucrose. Because sucrose, table sugar, is this a fructose molecule and a glucose molecule linked together in an acetal linkage. You will never, ever have to know this, but I'd highly recommend that you know, first of all, what is sucrose? It's made up of glucose and fructose. If on a test I were to put this and this, you should know how to write the name sucrose down, what it is. So all the starches and many of the complex sugars are polymers of fructose or glucose, mainly glucose, and also there are other sugars. And we call those polysaccharides. And the linkage is called glycosidic. I won't ask that. It's really an acetal or ketal. And what this shows you on here is starch is this many glucose. And you have amylose when it's the 1,4, which I showed there. If you throw in some of the 1,6, they call it amylose pectin. That I won't. But let me get to this slide in a second. All right. Now, what's the linkage holding glucose together in starch? An acetal. And for test number 2, you learned acid hydrolysis of an acetal or ketal gives back the aldehyde or ketone you would have used to make that acetal plus the alcohol you would have used to make that. And as you know, I don't show balancing, and you get 2 alcohols, we don't have to put it down. Now, if we look over here, what is the linkage in starch? This acetal. And if you break this, what do you get? Let's find out. You've just had breakfast and you had some starch, like a piece of toast or your cereal, whatever, and it goes into your stomach after you chew it. Hopefully you chew your food before you swallow it, otherwise you'll choke. My mother told me that, and I learned when I was about 2.5. She was right, and I learned that lesson the hard way. But anyways, starch, you're breaking the acetal linkage, and what do you get back? Glucose. Lots of them. And remember, in glucose, the alcohol and the aldehyde are connected together. So the next time you're eating something with a carb in it, carbohydrate, a starch, and you swallowed it after you chewed it, well, what's going on in your stomach? Acid and water, acid hydrolysis of an acetal. Now, leaving my class, there are a couple things you should know. And one of them is how to describe with words and a general reaction what happens when you eat a starch or a carb. And how do you describe that in words? Again, I'm going to be coming back to this. I went through a little quicker. It's acid hydrolysis of an acetal. And what's the general reaction? If you put an R prime here, that's okay too, but get back the aldehyde, if it's an acetal, plus the alcohol you would have used to make that. And that's what's happening when you eat anything with starch. Why is glucose the most abundant sugar? Because animals, like us and humans, when we consume starch, and plants too, how do they store energy? Starch. How do they get it back? They break it down to glucose. Now, this is starch. And notice the oxygen bond between the two molecules of glucose are below the ring. In cellulose, which is what you're writing on now, which is a carbohydrate, I don't think you realize paper is a carbohydrate, it's different. One bond is above and below. And because of that difference in stereochemistry, it takes a lot longer to break that bond doing the acid hydrolysis with an acetal and cellulose than starch. Which is why if you're starving and you eat paper, it's not going to keep you alive that long because it doesn't stay long enough in your stomach to break down. Same thing with grass or wheat, or not wheat, hay. But if you look at a cow or a horse or an elephant, what did they have? Monster stomachs, or in case of a cow, and now I'm well beyond my level of animal husbandry, 4 stomachs, because that gives that starch, carbohydrate, longer time to react with acid and break down to glucose, and it needs it. And with that, I'll see you on the F lab today in a couple of minutes. If you don't, I'll see you on Monday. Remember Monday, lipids.